For thousands of years, the night sky has inspired curiosity, wonder, and imagination. Long before the invention of telescopes, ancient civilizations watched the movements of stars, planets, and constellations, searching for patterns that could explain the world around them. These early observations laid the foundation for astronomy, a field driven by one of humanity's deepest desires: the need to understand our place in the universe. As knowledge expanded, so did our ability to explore the cosmos. Mathematical models revealed the motions of planets, powerful telescopes uncovered distant galaxies, and scientific discoveries gradually transformed our understanding of reality. Yet with every answer came new questions. The universe consistently proved to be more vast, more complex, and more mysterious than anyone had imagined. Today, humanity stands at a remarkable moment in this journey of discovery. We possess technology capable of observing objects billions of light years away and detecting light that began its journey across space before Earth even existed. Among the most advanced tools ever created for this purpose is the James Webb Space Telescope, an observatory designed to look deeper into cosmic history than any of its predecessors. Unlike traditional telescopes that primarily observe visible light, the James Webb Space Telescope specializes in infrared astronomy. This capability is crucial because the universe is expanding. As galaxies move farther apart, the light traveling between them becomes stretched, shifting toward longer infrared wavelengths. Much of the oldest light in the universe can no longer be seen with ordinary optical instruments. By detecting infrared radiation, Webb allows scientists to observe some of the earliest galaxies that formed after the birth of the cosmos. The telescope itself is a remarkable achievement of engineering. Its massive gold-coated mirror, consisting of 18 precisely aligned segments, gathers faint light from distant objects with extraordinary sensitivity. Positioned approximately 1.5 million kilometers from Earth, Webb operates in a cold and stable environment that allows its instruments to detect signals that would otherwise be overwhelmed by heat and interference. Before Webb began its mission, the Hubble Space Telescope had already transformed astronomy. Hubble's observations revealed that the universe contains far more galaxies than previously estimated. One of its most famous achievements came from deep field images, where the telescope focused on seemingly empty regions of space for extended periods. The resulting photographs revealed thousands of galaxies packed into tiny sections of the sky. These images fundamentally changed humanity's perception of scale. What appeared empty to the naked eye turned out to contain vast cosmic structures stretching across unimaginable distances. Every galaxy contained billions of stars, and around many of those stars, planets likely existed. The realization that the observable universe might contain hundreds of billions or even trillions of galaxies dramatically expanded our understanding of the cosmos. Yet even Hubble had limitations. The most ancient galaxies were often too faint and too distant for it to study in detail. Their light had been stretched beyond visible wavelengths, making them difficult to observe. This challenge motivated the development of the James Webb Space Telescope. When Webb began sending back data, astronomers quickly realized they were witnessing something extraordinary. Images revealed galaxies from an era when the universe was only a small fraction of its current age. Scientists expected many of these early galaxies to appear primitive, irregular, and relatively undeveloped. Instead, some appeared surprisingly mature. Several distant galaxies displayed organized structures, significant stellar populations, and evidence of chemical enrichment. Elements such as oxygen, carbon, and nitrogen were detected far earlier than many models had predicted. These elements are produced inside stars and distributed through space when stars die. Their presence suggested that multiple generations of stars may have formed and evolved in a relatively short period after the Big Bang. These findings have sparked intense scientific discussion. They do not overturn established cosmological theories, but they do challenge assumptions about the speed at which galaxies formed and evolved. Researchers are now working to refine existing models and better understand the processes that shaped the early universe. These findings have sparked intense scientific discussion throughout the astronomical community. While they do not overturn the fundamental principles of modern cosmology, they raise important questions about how accurately current models describe the earliest stages of cosmic history. For decades, scientists have relied on sophisticated simulations to understand how matter evolved after the Big Bang, gradually forming stars, galaxies, and the vast structures observed throughout the universe today. Many of these models suggested that the first galaxies would emerge slowly, requiring hundreds of millions of years to accumulate enough mass and complexity to resemble the mature systems seen in the modern cosmos. However, observations from the James Webb Space Telescope have revealed a more complicated picture. Some of the earliest galaxies appear unexpectedly bright, massive, and organized. Rather than looking like primitive building blocks in the process of formation, several seem to possess characteristics associated with much later stages of galactic evolution. This has led researchers to reconsider whether the processes that governed the young universe may have operated more efficiently than previously believed. One possibility is that star formation occurred at an extraordinary rate during the universe's first few hundred million years. Under this scenario, enormous clouds of gas rapidly collapsed under gravity, creating stars at a pace that exceeded expectations. These stars would have produced vast amounts of energy and quickly enriched their surroundings with heavier elements. Such rapid development could explain why some early galaxies appear surprisingly mature despite their young age. Another possibility is that our understanding of galaxy growth remains incomplete. Current models incorporate countless variables, including gravity, gas dynamics, radiation, and the influence of dark matter. Even small adjustments to these factors can dramatically alter predictions about how quickly structures form. The new observations may indicate that certain processes played a more significant role in shaping the early universe than scientists previously recognized. Researchers are also examining whether the earliest galaxies contain populations of stars unlike those commonly observed today. The first generations of stars are thought to have been far larger, hotter, and more luminous than modern stars. If these ancient stellar populations were more common than expected, they could help explain the brightness and apparent maturity of some distant galaxies. Understanding these stars is critical because they help transform the universe from a relatively simple environment into one capable of producing planets, complex chemistry, and eventually life. At the same time, astronomers remain cautious. Observing extremely distant objects is inherently challenging. The farther we look into space, the further we look back in time, and the fainter the signals become. Interpreting these observations requires careful analysis, and researchers continue to gather additional data to verify initial conclusions. Science advances through evidence, testing, and refinement, and many of the questions raised by Webb's discoveries are still being actively investigated. What makes this period particularly exciting is that astronomy may be entering a new phase of discovery. Throughout history, major advances in observational technology have often revealed phenomena that existing theories could not fully explain. Rather than weakening science, these moments have typically led to deeper understanding and more accurate models of reality. The discoveries made by the James Webb Space Telescope may represent another such turning point. As more observations become available, scientists hope to build a clearer picture of how the first galaxies formed, how quickly stars enriched the cosmos with heavier elements, and how large-scale structures emerged from the aftermath of the Big Bang. Each new image contributes another piece to a puzzle that spans nearly the entire history of the universe. In many ways, these findings highlight the true nature of scientific exploration. The goal of science is not simply to confirm what we already believe. Its purpose is to confront nature with observation and follow the evidence wherever it leads. Sometimes that evidence reinforces existing ideas. At other times, it reveals unexpected complexities that challenge long-held assumptions. The discoveries made by the James Webb Space Telescope appear to belong to the latter category, opening new avenues of research and encouraging scientists to ask deeper questions about the origins of cosmic structure. Far from closing the book on our understanding of the universe, these observations remind us that many of its earliest chapters remain only partially understood. The story of cosmic evolution is still unfolding, and with every new observation, humanity moves one step closer to understanding how the universe transformed from a sea of primordial matter into the vast and intricate cosmos we observe today.